Okay, I think I need to do something with the Biot-Savart Law, so I will do a fairly simple thing. What I want to do is I want to look at something that looks a lot like this. We've got a plane that has a current going through it, some sort of current going, say, that way, and we want to figure out what the field is, right? We could do this with Ampere's law. Maybe I'll go ahead and do another Ampere's law one just to show the similarity, but probably you should do that. Probably you should go ahead and do the Ampere's law and see how much simpler that is in this particular case. But here we'll just have a plain sheet here that has a surface current K going through it. All right. And so what we'd like to do is, just formalize all that. So given, what are we given? A conducting sheet is what I've got over there, because it's conducting current, so it's a conducting sheet. And it has a surface current density. And we've said that certain current density is K. Right, we'll do a little more with it in a moment, but that's what we have to work with so far. And that's really all we need to know to specify the situation. Anything that we want to know, we can do from there with whatever we have, right? It's not a major issue. So what would we like to do? We'd like to find the magnetic field. So the magnetic field has these vector sources, which are current densities, right? So this is our source. This is the field that's proportional to the force, right? Or it would be proportional to a force if we had scalar sources. Instead we've talked about what the force is in this case, which is a little bit different because we only have dipoles. So our concept here is our Biot-Savart Law, right? And our equation is something like this. B is equal to some constant, which is mu naught over 4 pi, the permeability of free space divided by 4 pi, over the double integral over some surface S of the current density cross the direction from some point on here to wherever the field point is. So it's that direction over the square of the distance, ds, right? So that's what we've got. That's what we've got to work with. Just like we did before, we really have to worry about the vectors in this case, right? We have to know exactly where everything is so we can figure out these things. So the setup here is going to be critical, right? Our setup will be critical, and we've got basically three things to worry about. Where are the points on the plane? Where is the field point? And then, what direction is the current? So if we specify all three of those things, we've specified the problem. So I guess the first thing is, where is the surface? So we're going to place the surface in the simplest place, and that's in the XY plane. Okay. Then, let's just stay with the surface. The current is going through the surface, so let's orient the current in the Y direction. So these are basically the same thing as what I've drawn here. We'll get to a more specific drawing in a second. And then we want to try to place our field point in the most symmetric place we can, which will be on the z-axis. Okay, so our vectors in this case for our plane, we have a position s, little s, on the surface, and that's going to be somewhere in the xy plane. So x in the some distance x from the origin in the x hat direction plus some distance y from the origin in the y hat direction. We want to orient the current, so the current density J is going to be equal to K times the delta function of Z in the y hat direction. We just said it's in the y hat direction. We've mostly used step functions in this case, or piecewise functions, excuse me. So we'll do it this way. So this is K in the y direction when Z equals 0. And it's 0 when z is not equal to 0. That's what the delta function means. And for the point on the z-axis, z is equal to z hat. Right? So if we draw this out, right? What we do in this case when we draw things out is we use, we want to put some axes in here. Right, so there's our z-axis, there's our y-axis. This is a right-handed coordinate system, right? So there's a y-axis that we can use with impunity, and here's an x-axis to make everything look right. We said k is in the y-hat direction. We don't have to actually draw that on this drawing. What we really care about in this drawing is where all the points that we have to integrate are and where they are with respect to the field point. So the points we're going to integrate are all in the xy plane, right? So we can draw this out like this. This will all look really, really good. So something like that. So that's our xy plane, and that's our surface that's carrying the current. And then up here on the z-axis somewhere is our field point, right? So some point on the surface S is going to be like one of these things here. So this is S here, right? And then this is Z. So that's S, which doesn't show up very well. S is that way, Z is that way, and from S to Z is going to be this R, okay? So we'll deal with that in just a moment. So this is the drawing that goes along with the setup. So I think you can go ahead and you can see how this is laid out. Maybe I wasn't as systematic about this as I should have been previously. But this is how you get from the setup to the vectors to the drawing. Generally, I'd probably do the drawing and then do the setup describing what I actually drew. Because I think I and most people are sort of visually oriented, and it's easier to do this than to do the setup, except in very, very simple situations like this. And this one, you know, you should be able to do the setup in your brain without actually drawing things out. But when you get more complicated situations in the future, then you'll have to spend more time drawing. So now we've got all of that ready. We need to have a strategy for solving this, right? So our strategy for solving this is, well, first we have to find R. So we'll have to determine this vector R, right? And ancillary quantities. There's some other quantities associated with the distance R that we'll have to worry about. Let's cut that out like that. 2, we'll need to determine the limits of it, right? The limits of integration. That's very, very important. 3, we'll write the integral and simplify it. And I think that's actually as much as I'll get done on this page, right? And where is that? Oh, that's getting pretty close down there. After I'm done with that, we'll have to go to another page, I think, and we'll evaluate the first integral, because we've got a surface, so we're going to we've got it's a two-dimensional integral, so we'll have to integrate twice. And this will be in the y direction, probably, I think. Let me check. No, let's do that in the x direction. And then we'll evaluate the second integral. Okay, and that'll be in the y direction, and that will actually get us our answer. We'll be done at that point without anything more to really worry about. But let's do the setup here on this sheet before I move on to the other sheet. Okay. Let's see. Yeah, at this point we are calculating, right? So we're going for our answer. First, our distance from here to here, r, is z minus s. From s to z is z minus s, right? So that's going to give us minus s, so minus x, x hat, minus y, y hat, plus z, which is plus z, z hat. This is about as easy as it gets. And that gives us a magnitude of x squared plus y squared plus z squared. And this guy, remember, is just this divided by that, right? So r hat is just the vector r divided by the magnitude of r, the displacement divided by the distance. Then we want to determine the limits of integration. Well, where does this plane stop? That's the question, and the answer is it doesn't stop anywhere. So x is going to be from minus infinity to infinity, and y is going to be from minus infinity to infinity. Okay, so those are the limits of our integration. So now we write our integral and we simplify. So b is equal to mu naught over 4 pi, right? I said our limits of integration for this guy are minus infinity to infinity in both directions. And I'll do j over r squared cross r hat. Let's see. R squared is this thing squared, so that's x squared plus y squared plus z squared, right? All over j, which at z equals 0 is k in the y hat direction. Okay, that's good. Cross this divided by that, which is minus x, x hat minus y, y hat plus z, z hat, right? And then we have our square root of x squared plus y squared plus z squared, because Pythagoras was cool. Okay, and then whatever way we're going to integrate this, I said first x then y, so dx dy. Okay, so everything's looking pretty good. Now we have to simplify that, right? So let's get as much room as I possibly can and see what we can do. I guess the first thing to do is to go through and do the cross product. When we do the cross product, k is a constant, so it comes out. So we have equals mu naught k over 4 pi. Okay. All of these things are going to come together, so we're going to have an r cubed, and r cubed gives us the sum of the squares, x squared plus y squared plus z squared to the 3/2 in the denominator. As for the cross product, we have y cross x, which is minus z, so that means we have x z hat, right? And then we have y cross y, which is 0, so that we don't have to worry about. And then we have y cross z, which is plus x hat, so plus z x hat, dx dy. And now if we look at this, z is just a constant, so we don't have to worry about that. This is called an even function, so that means on this side in both x and y. So this means the value here is going to be the same as the value over here, and the value here is going to be the same as the value over here, right? The value here is going to be the same as the value back here. So when we do this reflection here, when we do this reflection, the value of this function stays the same. So if we have that, then we integrate from 0 to infinity. It's equal to twice minus infinity to infinity, because whatever we have here sums up there. If we multiply that by x, which is an odd function, then this is minus that. And so when we integrate, or I guess, yeah, x is along here. This is minus that. So the value here is minus the value there. Add this plus this, it's equal to 0. So in fact, the z component's going to cancel out. We don't have to worry about the z component. We only have to worry about the x component. Right, so I just said that's 0. The x component, and this z is independent of everything else, so that comes out. So we end up with that coming out. We go 0 to infinity in both of these cases. That's multiplying by 2 twice. So we have mu naught k over 4 pi multiplied by 4z x hat, integral from 0 to infinity twice, right? 1 over x squared plus y squared plus z squared to the 3/2 dx dy, and this is what we're going to work with on the next page. So we're going to pull this on over to the next page after we cancel out these 4's, and we'll be good to start. So and so there that is. I guess that's off the page. I'm sorry, that was off the screen. So we'll get back to that in just a moment, maybe after I pour myself a nice new glass of scotch. Talk to you in a second. Okay, let's see what we've got here. All right, that's about the best I can do. So what we're looking at again is, we've got this plane here, this infinite conducting plane in the xy plane, I guess infinite conducting sheet in the xy plane that has that's carrying some surface current density K in the y direction, and we're looking at what happens to a field point up here, right? And if we're looking at some point here on our xy plane, then this is our radius vector r. And we don't really have to worry too much about that because we've already done all that work on the previous page. Feel free to go back and see what's going on there if you're a little bit confused. So what we've got left to do is this integral, right? We have some constant out here which includes our direction. And the definite integral from 0 to infinity in the x and y directions of x squared plus y squared plus z squared to the minus 3/2. So that's just 1 over this r cubed. We've actually seen this integral before. We saw it when we were doing Coulomb's law. It's nothing astounding, and everything that I'm going to do from now on is really it's calculus, but it's not really any different from algebra. This is all the denouement. I can't pronounce it, so I should just stop trying. So anyways, we're going to go on with this integral. So first thing I'm going to do is I'm going to pull out everything that I can except the x in here. Actually, I can't really pull it out, but what I can do is accept the x, right? What I can do is I can get this into a form that's a little bit easier to integrate, right? So we want to integrate the internal part here, which is going to now be 1 plus z squared over y squared, or x squared over y squared plus z squared, x squared over y squared plus z squared, and all that to the 3 halves. Got our dx and our dy, because we still have to integrate this out, right? So when we do that, we don't get anything particularly strange. We have a pretty good idea of what's going to happen with that already. 4kz x hat over pi. We still got our integral from 0 to infinity of 1 over y squared plus z squared to the 3 halves. This is multiplied by 1 over this constant, which is to the square root of 1 over this thing, which is y squared plus z squared to the 1/2 here. It's the square root of that. And then we're left with figuring out what the value of this thing is. The square root of x squared plus y squared plus z squared over x, evaluated at x equals 0 and x equals infinity, dy. So there are 2 spots on here at x equals 0. This is the denominator is non-zero. The numerator here is 0, so it's 0 at infinity. We can ignore this. We have basically just the sign of x, right? Going on there. And the sign of infinity is just going to be 1, so we have this thing is equal to 1. We don't have to worry about that anymore, and we cancel that stuff out, and now we're at mu naught kz over pi blah 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 0 to infinity 1 over y squared plus z squared dy. And this is one of these things that after a while you get really used to. This is just going to give you the arctangent, so we'll have to go with that mu naught kz over pi x hat. And so this also has a constant 1 over the absolute value of z times the arctangent of y over z, evaluated at y equals 0 and y equals infinity. So that's equal to mu naught k over pi times x hat times z over the absolute value of z, which is just the sine of z, right? Times the difference between the arctangent at infinity minus the arctangent at 0. Right? This guy is 0, and this is pi over 2, right? So we'll cancel out this pi, we'll put a 2 in there instead. This is a sine of something, so we have mu naught k over pi, or over 2, excuse me, times the sine of z. Yeah, so this is a 2 and this is a z. in the x hat direction. Okay, and that's pretty good. If we could write this piecewise, because I know you prefer the piecewise. That's mu naught k over 2 x hat when z is greater than 0, and mu naught k over 2 minus mu naught k over 2 x hat when z is less than 0. Okay, so that's our answer right there. And that makes sense. So we said we had this right-hand rule, right? Which means if we come this way, come up, right? K is this way is, yeah, let's do it this way. K is this way is our, this way up along the z-axis is our radial point, and that way in towards you, along this x-axis, this is the way the field is going B. Down here, the field is going in the minus x direction, which is exactly what we said here. We get all that for free, right? Free. It's good. It's beautiful. We got the directions for free, as long as you do everything right. So that is how to use the Biot-Savart Law. It's nice and simple. There's nothing particularly complicated about it, so you should be more or less ready to use it at a moment's notice, because you're going to have to use it at a moment's notice. This is what that magnetic field looks like when you plot it out in as a function of z right there. So everything's good, and I will see you in class.